Okay guys, so today we're going to be discussing entropy, and by the end of this lesson you should understand kind of what entropy is and how it's calculated. So first off, the second law of thermodynamics states that the entropy of the universe is always increasing. So that already makes entropy very unique. Enthalpy is based on energy, right? And so we know that there is a law of conservation of energy, and that the amount of energy in the universe is finite. It's never created, it's never destroyed. Similar to matter, matter is never created nor destroyed. There's only a certain amount that exists in the universe. However, entropy is always increasing. So let's talk about why that is, right? First off, entropy is a measure of molecular randomness or disorder. Okay, so basically the universe is becoming more random, specifically in the positions that we can find molecules. So as positional probability increases, entropy increases. Why is that? Well, think about the universe itself, right? At the beginning, supposedly, right, this is one of the theories, right, the Big Bang theory, is that everything started in one place, and then there was an explosion where all of the matter and energy of the universe was sent flying, right? And so the universe is constantly expanding. As all that material travels outward from the Big Bang, all of that material traveling outward just keeps expanding the universe larger and larger. So the space that the universe takes up keeps increasing. And so things keep moving around within that larger space. And so there's just more and more random positions available. Think about it as you're rolling one die, right? Then you're rolling 2 dice, then you're rolling 3 dice, then you're rolling 4 dice. There's just more and more different combinations of numbers possible, right? As you increase that space in which the molecules can operate, you're increasing the different numbers of positions that they can be found. And so the universe tends to favor things that are more disordered, because the universe itself is increasing in disorder as it grows, okay? So some really important things to keep in mind when we're predicting entropy changes. We're going to have increases in entropy. By the way, that's going to be a positive delta S, right? S means change in entropy. And so some of the positive changes, the changes that are going to cause more disorder, are going to be phase changes. Specifically when we go from solid to liquid to gas. Okay, so as we go from material that is found in a solid where the particles are kind of locked into place, then we move to liquid where the particles are able to slide past each other, so they're able to move a bit. That increases the randomness of the particles, right? They can be found in a bunch of different positions as a liquid. As a solid, they're kind of almost locked into one place, right? Now the electrons are still moving, so solids themselves will still have entropy values. They're not completely free of entropy. Anything that has electrons moving is going to have an entropy value. We'll get to that more later, but even solids have some entropy. And it increases as the distance between particles increases, right? Just like as the universe increases and those particles are able to take up more space, then their positional probability increases. So as we go from liquid to gas, those particles are then able to bounce off of each other and move all over the container, so their entropy increases. Similarly, if we dissolve something, if dissolution happens, right, then those particles go from being near each other to being broken up and spread across that solution, right? Also, if we're looking at a chemical reaction and we notice the formation of a gas, then we are creating a more disordered environment, and so that's going to be an increase in entropy. And then if we have the opposite of this, then those are going to be decreases in entropy. Those would give us negative entropy values. Okay, so when we calculate entropy, we use this equation. The change in entropy is equal to the change in enthalpy divided by the temperature. And a couple of important things. Temperature has to be in Kelvin for this, so make sure you're using Kelvin. And enthalpy values are generally given in kilojoules per mole, right? Well, entropy is generally going to be in units of joules per mole times degrees, Kelvin, right? Joules per mole Kelvin. So make sure that you convert your kilojoules to joules, and then you divide by the temperature in Kelvin. And so that's what we're going to do in this example here. It says to calculate the entropy change of the following reaction at 25 degrees Celsius. And so they've given us this chemical reaction, and then they're asking us to find the entropy. The enthalpy is given here as a part of the equation, and you guys should understand from our previous studies of enthalpy that when it's found as a part of the products, that means that it's negative. So our delta H, there we go, is negative 125 kilojoules. Okay, our temperature is 25 degrees Celsius, so I'm going to add 273, and that gives me 298 Kelvin. All right, so basically I'm going to take my enthalpy and divide it by 298, and that's going to give me entropy. But I do have to convert kilojoules to joules first. So negative 125 kilojoules, draw my line, drop my unit. 1 kilo anything is equal to 1,000 of the base unit. So in this case, 1 kilojoule is equal to 1,000 joules. And so I've got negative 125,000 joules. Okay, so I'm going to take negative 125,000 joules. I'm going to divide that by 298. And so when I do that, I end up with 41, and actually, it's negative enthalpy divided by temperature. So if I have an exothermic reaction, then I'm actually going to end up with a positive value for the entropy. So positive 41.9 joules per Kelvin, and actually, this was kilojoules per mole, right? So moles is on the bottom of this unit, and so I need to put moles on the bottom of this unit, okay? So my answer should be 41.9 joules per Kelvin times mole, okay? So then an alternate way to calculate the entropy of something is to use the Big Mama equation, the thermodynamics equation. Keeping in mind the third law of thermodynamics. So the entropy of a perfect crystal at 0 Kelvin is 0, and that's about it. So a perfect crystal is a solid with all of the particles locked into a specific position, and at 0 Kelvin, guys, at absolute 0, nothing is moving, including the electrons. So there is no kinetic energy whatsoever. The electrons are not moving. That's the only thing that's going to have an entropy value of 0. Otherwise, if the electrons are moving, then there's going to be some randomness in the positions that you find the electrons in, and so it's going to have an entropy value. So only things at 0 Kelvin, which basically is nothing, everything has some kinetic energy, right, is going to have an entropy value of 0. The only other thing that has an entropy value of 0 that I can think of is the hydrogen ion. The hydrogen ion also, if you look it up, has an entropy value of 0, and that's because it has no electrons. Other than those two things, everything is going to have an entropy value. Unlike enthalpy, elements have standard entropy values. They're going to have values in the back of the book because they are disordered. Okay, everything, even elements, are going to have entropy values, okay, because everything has electrons that are moving and everything has some amount of disorder, okay? So again, we use the thermodynamics equation. The sum of the products minus the sum of the reactants is going to give me the overall enthalpy change for the reaction. So if I was going to do that for this example problem, I look at the equation. What I would do is I would look in the back of the book for my standard entropy values, and I would start going ahead and multiplying these out. So remember that when you have coefficients in your equation, the values given to you under standard conditions are per mole. So if there's 2 moles of it in the equation, I have to multiply that value by 2. So I would do 2 times the value for SO2 gas, and make sure you're using the correct state of matter. If sulfur dioxide has a liquid value or a solid value, it'll be different. So it's specific to the state of matter. Make sure you're looking at the correct one. So 2 times the value for SO2 gas plus, because it's a sum, 2 times the value for nickel oxide gas, no, solid, there it is, should be a solid, minus the sum of the reactants. So 2 times nickel sulfide, solid, there it is, plus 3 times the value for oxygen gas. And so that's different. When we did enthalpy, we didn't worry about the elements. But when we're calculating entropy, delta S, since oxygen has electrons, it is going to have a value for entropy. So make sure that you look it up. Don't leave them out for entropy. Okay? And so I'm not really going to look these up and do the math, but that's exactly how you would set it up. We've used this equation before. Just remember that the big difference for this is that we're not going to leave out the elements. Elements have entropy values in these equations. Okay? So good luck with your work.